All right, so this week we're going to be talking propositional logic. This is going to be the math behind true and false, your Boolean statements, your if statements, things of that nature. This is extremely important in the field of computer science because branching code is everywhere, and there's also some lower level implementations of propositional logic and predicate logic, which you'll cover in your discrete computational structures class. So, for this lecture, we're going to look at just what propositional logic is, how it's used at high and low levels, logical operations, properties, and we're going to look at truth tables. Truth tables are going to be the focus of your assignment for this week. So we'll put plenty of focus on those. So, propositional logic, you can think of this as the underlying math of true and false statements. We take these statements and we combine them in many different ways, and we synthesize a new statement. A word you've heard several times already, you're going to hear it even more, atomic statements. These are singular, indivisible logical statements. These are represented mathematically using variables such as p, q, and r. If you have more than 3, you can do s, t, u, keep on going. Operations and properties, as it says here, are combined to synthesize new statements. And this is where truth tables come in that these take a look at every possible combination of atomic statements and show what new information is synthesized from them. And by using these, we can verify that our if statements are other logical operations. We can confirm that these are created correctly and there's not going to be any logical errors or holes in our logic. So, how is it used? So, at the high level, propositional logic is the foundation of if statements. You can have if statements. These are conditional operations that can take one or more true-false statements to evaluate, and these can go in many different directions. And we use propositional logic to understand all the different directions these can go in and ensure that we have accounted for all of them. So if you think about an if statement or a conditional statement with one Boolean condition to check, okay, that's going to go one of two ways. It's either going to be true or false. What if you have 2 conditions that you want to check? Well, that can go 4 ways. And if you have 3, that becomes 8 different possible outcomes. And that's just a very basic, very simple explanation of it. It can get far more complicated than that. I have had to do statements with as many as 5 conditions, all working in tandem, all grouped in different ways, and these naturally produce more and more complicated situations with more possible outcomes. So it's crucial that we understand how to do this. You may not necessarily find yourself doing truth tables when you're creating your conditional statements, but the understanding you gain from them can be a huge help. On the lower level, however, we use propositional logic for logic circuits. We look at combinational logic, taking statements like you see we have A, B, and C here in this chart. These would, of course, map to P, Q, and R respectively. We use gates to show these statements being combined, and eventually we reach a solution that is represented as Q. This is very common in designing computer chips. If you were to work for a company like Intel, it would be important that you understand this sort of thing, how we use logic gates, and you'll be expected to learn this when you get to your computer architecture class, and you're going to be drawing a lot of logic circuits like these. So when we talk about Boolean things, when we talk about propositional logic, combinational logic, it helps to remember that true, false, on, off, yes, no, 1, 0, these are all basically the same thing on a computational level. It either is or it isn't. It's as simple as that. Now, when we start talking about our logical operations, there are several that we have to work with. So let's take a look at each of them. The first is going to be your conjunction, or your AND. You can represent it with capital letters A and D. You can represent it with 2 ampersands, or you can use an asterisk or a multiplication symbol. So, for an AND statement to evaluate as true, both P and Q must be true. If either one or both are false, then the statement is false. Now we have the inclusive disjunction, or inclusive OR. This can be represented with capital OR, 2 vertical bars, or a plus sign. And while this reads, well, we might think of the OR as, it needs to be one or the other. In computation, a typical OR can also be read as AND OR. So the only situation in which an OR statement is false is when both are false. If either is true, if both are true, the inclusive OR statement evaluates to true. Next, we have the exclusive disjunction, or XOR statement. It can be written as capital XOR, can be a caret symbol, that's this upward arrow, or it can be this circle with 2 lines dividing it into quarters. I don't know what that symbol's called. It's just, to me, the XOR symbol. Now, this is pure OR. In linguistic terms, this is your typical OR, while in linguistic terms, your inclusive disjunction is AND OR. And this evaluates to true when only one of your 2 statements, P or Q, is true. If both are true, if both are false, then it evaluates to false. In mechanical, electrical terms, you could think of this like a 3-point switch. So you have a room that has 2 light switches on either side that control all the lights. If they're both pointed up, then the lights are off. If they're both pointed down, the lights are off. If one is up and the other is down, then the lights turn on. And that's how your 3-point switch works, and that's how your XOR statement works. Now you have negation, or not. It can be represented with capital NOT, it can be an exclamation mark, or it can be a tilde mark. And this is pretty simple. It only takes one statement, P, and it evaluates to whatever P is not. So if P is true, not P is false. If P is false, not P is true. You will see some of these symbols reappear when you do programming. So in Python, lowercase and or are used for, well, and or. In C++ and Java, the double ampersand, double vertical bar are used. And I believe, I need to refresh myself, we'll do that prior to the examples. Regardless of language, whether it be Python, C++, Java, the upward arrow or caret symbol is your XOR. Negation in Python is lowercase not. In other programming languages, C++, Java, it is the exclamation mark. Another type of statement that you'll see is the negations of and, or, and XOR. These are NAND, NOR, and XNOR. A silly thing. For some reason, my brain always reads XNOR as snore. But that's aside the point. these are the opposites. So if an AND statement would evaluate to true, then NAND would be false. If OR would be true, NOR is false. If XOR is true, XNOR is false. And there's something special about the NAND operation, and that is it is more efficient to create logic gates in I don't even know, maybe all cases. These can be used exclusively. So if you have a logic circuit that is entirely comprised of NAND gates, this can perform better than a simpler logic circuit with a combination of different gates. This is better performance than using a variety of gates because it's having to load in fewer operations. So because you're using only the one thing, you're using NAND or not AND, you improve the performance of your logic circuit. And here is the explanation in terms of their truth tables. So you have P and Q. If P and Q are both true, then NAND is false. Otherwise, it's true. So it is, again, the exact opposite. NOR, if P and Q are true, then it's false. If either P or Q are true, then it's false. And if both are false, then it's true. And then your XNOR, if they match, then they are true. If they do not match, they are false. That's the easiest way to think about XOR and XNOR. XOR, if they do not match, then it is true. Otherwise, it's false. And then the opposite for XNOR. Now we have some properties of our logical operations. And boy, don't these look familiar. So we have our commutative, associative, distributive. These are the same as they were for for sets. So I'm not going to go over those again. We have the absorption law that states that if A or B and A, if we have an AND of A being applied to A or B, then that just equals A. And if we flip it the other way around, if A and B or A is our expression, then it's still going to equal A. Idempotent, this one is another one we've seen already, so I'm not going to go over it. A very important one, though. The main one I want you to focus on is this last property here. This is De Morgan's law. Now this you'll see coming up quite a bit, and that is if you negate A or B, if you negate the operation A or B, and you see I'm using the grave accent here, that is also an acceptable symbol. That is equivalent to not A and not B. Conversely, the negation of A and B equals not A or not B. This comes up a lot more than you think. So it's very important that you memorize that one. If you only memorize one of these 6 properties, let it be De Morgan's law. Now let's switch gears to talking about truth tables. You saw them already on slides 5, 6, and 8. But here we're going to talk about how we can use them to evaluate our expressions. So what you're going to do is you're going to list all possible combinations of your atomic statements, your P, Q, R, S, whatever, and you're going to evaluate them. So again, we list everything and then we evaluate all of them. This sounds like it'd be really tedious, but once you get the hang of it, you will fly through your truth tables and they'll just take a matter of seconds to finish. Atomic statements always go on the left. Then you have the pieces of your compound statement in the middle, and then your final evaluation on the right. So let's have a look at this one here. So let's say we want to evaluate P and Q XOR Q or R. Okay, this looks pretty complicated, but what we're going to do, we're just going to list all combinations of P, Q, and R. There are 8 of them. Remember that however many atomic statements you have, the number of rows in your table is going to be 2 to the n power, n being your number of atomic statements. In our case, here, we have 3, so 2 to the third is 8. And those are true, true, true on the first line. On the second line, true, true, false. Then true, false, true. True, false, false. False, true, true. False, true, false. False, false, true. And false, false, false. Now, let's look at our smaller compound statements here. Think of these next two as simplifying our operation. So we have P and Q. First row, P and Q are true, so it's true. Same for the second row. And every row below that, either P or Q or both are false, so the rest of them evaluate to false. And if we look down, or we look over at our next one, Q or R, there are only 2 that are false. That is row number 4, which is true, false, false, and row number 8, which is false, false, false. So, because those are the only 2 where our statements do not give us an OR evaluation of true, you have true, true, false, or true, 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 false, true, 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 false. Now we take those 2 and we XOR them together. So which of these do not match? Okay, so we have true and true, that's false. True and true again is false. True and false, or false and true, is true. False and false is false. False and true is true. False and true again is true. Then we have false and true. I made an error there. That is actually supposed to be true. So row number 7, where you see false and true, you XOR those together. You should get true, but I've made a mistake and put false. False and false, of course, they match, so they are false. And we're going to look at more examples as we go along. So stay tuned for those. We're going to do a lot of examples just because this is important. So in the next lecture, that's going to be a bit long, we're going to evaluate a bunch of truth tables. So stay tuned for that.